inviting. First of all, I would like to thank Mr. Nikhil from Petroleum Engineering Association for inviting me for this event. It has been around 2 years since first time we in touch, but finally we made it and we found a good time. I was busy before, and now I am happy to share with you my experience in 3D geological static modeling. And as Nick had already introduced to you, I have 20 years of experience working worldwide, and mainly with the Schlumberger, where I worked like 10 years. And then I worked 8 years with Saudi Aramco. Those are the biggest companies in the oil industry. And currently I'm based in Istanbul. Since 2 years, I'm working with a company here in Istanbul doing the similar thing with some more tasks I'm doing right now. So before we start, I will just say something about the 3D geological static model. It is very crucial process in the oil and gas industry, not only in the oil and gas industry, but also as well as in the other fields such as mining and groundwater management. Also in the renewable, they are using the static modeling, and for CO2 storage, they are using the static modeling for their project. So it's kind of very important and crucial process in many domains and many industry. This technique involves creating detailed 3D, or three-dimensional digital representation of the subsurface geological formation, including distribution of the rock properties, fluid content, and structural features. By leveraging advanced computer software and some advanced data analysis technique, geologists and engineers can gain a comprehensive understanding of the subsurface, which is essential for making an informed decision about exploration, development, and production activity. So for today's workshop, I start my presentation with the training agenda, as you can see here. So we will start by defining what is the 3D geomodeling or 3D static geomodeling or reservoir modeling and why. And after that, I will show you the reservoir modeling workflow, and you can see it here. I hope you can see my pointing. You can see from this sketch that we have the general workflow of the 3D geological modeling. Then I will go in detail with the data management and preparation, followed by structural modeling, facies modeling, property modeling, and I will end it by the volumetrics, calculation. After that, we may do some, uncertainty analysis and model upscaling to prepare the model to go to the dynamic modeling stage. In the end of the presentation, I will show you some short modeling demo using one of the common software in the oil and gas industry. I will show you a short demo about all of these or most of these processes if time permits. So now, what is the 3D geological static modeling? It is, if we want to understand that, so it is kind of, you create 3D, kind of digital representation of what is going on in the subsurface. In the subsurface formation, which having the oil or hydrocarbon bearing formation. So you are building kind of 3D structural, digital representation of the subsurface. And these models are, integrate using many type of data, as you can see here. We using the seismic data coming from the seismic survey. We are using the well logs coming from the wireline logging, or it depends if it is wireline logging or if it is LWD logging. So we are using the well logs coming from this type of the data. Also, core samples and core plugs and core analysis are used here to build the geological modeling, specifically in the facies modeling phase. Core is very important. And also using the geological interpretation, geological sedimentological conceptual modeling. It's used to build the 3D geological static modeling. So the aim of this process is to depict the distribution of the rock properties, fluid content, and structural features in the reservoir. And if you can see here, it's mainly, it is mainly using our main item or main rock and fluid property in the static model. As you can see here, it's lithofacies or lithology and facies, porosity, permeability, fluid saturation, and sometimes fluid pressure. And this is mainly before the production. And they are built using measured data as well as well location, as I mentioned before. It's using the well logs and other data, including core and seismic data and geophysical measurement seismic data. And as you know, the geophysical data having low resolution, so hence the static reservoir model are uncertain, and that's why I will end up my presentation by showing you some uncertainty analysis. And uncertainty is generally represented by ensemble of multi-models. We are building kind of, for example, 100 or more realization, depend on the project size, asset, timeline, deadline, all these things. So of the porosity with different spatial correlation. So now we said why we need the geological static model. So static model serve as the foundation of the dynamic reservoir, and as you can see here, it will assist the, it will be base of the dynamic simulation. So which is simulate, the dynamic simulation, which is simulate the flow of the fluid through the subsurface over the time by incorporating the geological data, seismic information, and well logs. These static model help identify the potential hydrocarbon reservoir and optimize well placement and assess the feasibility of production scenario. So it is a base of the dynamic simulation. Also, they maximize the information used to optimize the production. So you have a lot of data coming from different sources. So by building a static model, we will maximize the usage of this type of data. Also, reservoir property are a very critical factor affecting the production. So it's very important in that. Also, reservoir model, it's very helpful in, and one of the most important tasks of building the reservoir, static model, is to calculate the hydrocarbon volume initially in place. So this is very important step to make a decision, to put a plan for the management to make a crucial decision for developing the asset or not. So this is very important step. And moreover, they are play a very critical role in risk assessment, allowing companies to evaluate and mitigate the potential challenges coming from doing the business, such as drilling hazard or unexpected geological formation. So they are kind of they will help in assess the risk and uncertainty, as I mentioned here, in one of these items. And also they are improving the decision and economic forecasting. And in summary, geological static model are very, very valuable tools that enable a deeper understanding of the subsurface, ultimately leading for the more efficient and cost-effective exploration and development strategy. So they provide a comprehensive and integrated view of the subsurface, empowering decision makers, the management, to make an informed decision and choices to maximize the value of their asset. So now here I'm just saying why 3D rather than 2D. First of all, it is for visualization. So it is easy to see your spatial relationship between the data. So it will act as a kind of tool for quality control of the data. Also, structural modeling. It's 3D is good for building complex structural modeling. Can be now modeled rather than in the past where we just having like 2D map and make a decision based on the 2D map and 2D evaluation. So 3D will be very helpful to build the complex structural model. And also they can model non-vertical faults, better for volumetrics and correct connectivity for the fault blocks. Also, why 3D? Because they are doing building property model, so it will have more data to be integrated in the model, and hence will increase the heterogeneity possibility to build the model, especially in the carbonate. So where you have a very heterogeneous environment, so you need to have the 3D will facilitate your work and decision. And finally, it is for reservoir simulation. So simulation model is always a 3D, as you know, the flow, when you are modeling the fluid flow and all of this stuff, it is moving through the 3D direction. And also, I mean, better geological model, meaning that you have better history matching, and hence you will have better prediction. So now, if you go to the reservoir modeling workflow, you can see that geomodelers are working with multi-scale discipline. They are working with the sedimentologists who describing the core description coming from the core blocks and then core analysis. The geomodeler is working also with the petrophysicists who put the interpretation of the logs, and then the geomodeler will upgrade the logs to fill the cells. I will mention that, you will show that in the workflow. Also, the geomodeler is working with the geophysicists who are in charge for putting the interpretation from seismic data, who are in charge to pick the horizon, who are in charge for pick the fault and getting some seismic attributes to build it together in the geomodel. And also, the geomodeler is working with the reservoir engineer who is in charge for the dynamic flow modeling. And as you can see here, the geomodeler who is in charge for building the static model is kind of generated the model from different discipline, different domain, and at different scale, starting from core scale, logs scale, seismic, and where you upscale the logs here, and then you build the geomodel, and then finally you go upscale it again to make it up to reservoir engineering and dynamic simulation scale. If you see the workflow of the reservoir modeling, we start with the data preparation and interpretation. And after that, we go with the structural modeling, and then we build the facies modeling. After that, we do the petrophysical modeling, which is property modeling, mainly for porosity, permeability, and water saturation. After that, we do the volumetrics calculation. Then we do some uncertainty analysis, and we do some upscaling after we finish the model, upscaling the model to make it ready for the flow simulation, dynamic modeling, and post-processing. And finally, these models can be used for well-designed, well-planned, taking decision. Many objectives for this model can be used for many objectives. So now for the data management and preparation. So effective data management and preparation is very critical step in the 3D geological static modeling process. And this stage involves data gathering, organizing, and processing a wide range of geological, geophysical, and engineering data from various sources, including seismic survey, well logs, core analysis, production history. So many type of source of the data you are gathering here. And the goal is to create a comprehensive and integrated data set that accurately, or I mean with high resolution, to represent the subsurface characteristics and provide the necessary input for subsequent modeling and simulation effort. So you can see here we have data management task, which include, as I mentioned, data gathering, organizing, process geological, geophysical, and engineering data. We have data source. We have data preparation, which include the quality control, unit conversions, and normalization of the data. And reliability and uncertainty of the data must be carefully evaluated and addressed. As you know, grab in, grab out. So we need to spend quite enough time for data management and preparation. So, I mean, as I mentioned, data managing is kind of, they are typically include these tasks I mentioned. And the many, I mean, as you can see here in this sketch, you can see that how many data you have. We have seismic data, we have horizon, we have well, we have many data, we have conceptual model. There are many data you need to spend long time to make sure that they are good enough to move on to the next step, which is structural modeling. So the structural modeling. Structural modeling is very critical and crucial step in geological static modeling. It is focused in accurately representing the complex fault and fracture system that define the subsurface geology. So we have three main type of structural modeling. We may use a simple grid to build the structural modeling where we don't have faults. It is as you can see here from the picture. And we have another type which is called the corner point gridding, as you can see here. This is the classical process for making a structural model. And in the corner point gridding, you have certain steps you are going to follow, starting with the fault modeling, pillar gridding, making horizon, and then you making zone and layering. So I will in the next slide I will show you each step advantage and disadvantage. And in the demo, I'm going to show you one of these methods. Most probably I'm going to use the simple grid because of the time limit. If we have fault, it will take long time. So one of these methods will be demonstrated in the software. And the third method for structural modeling is the structural framework, which is allow the interpretation data to be combined together with the to construct a structural model. And framework is kind of solve a lot of complex problem boosted from the complex fault system. If you have kind of very complex, huge number of fault system, you may consider a structural framework. Now, in the next slide, you can see that we have advantage and disadvantage of each method. So in the simple grid, it's simple grid as from its name. It is good for velocity model. It is easy, fast from its name. It is a simple grid. And having view process dialog. So it is very simple, advantage. However, they have some limitation, as you can see here. Mainly they are using vertical pillars, no fault and no segment. So if you have kind of layer cake model or reservoir, if you don't have fault, you just go ahead with the simple gridding. If we look at the corner point gridding, however, there is some advantage, which is coming from they can handle the deviated and truncated pillars. They are good for standard model, and they are good for grid with the fault. I mean, if you have fault, this is the best way, one of the best method to use for fault modeling. However, there are some limitations. They need time. You need to spend time, and it needs multiple process, many manual work here. And sometimes it is difficult to handle complex structure. So for the structural framework, the advantage of the structural framework, they are handling the complex structural modeling, and they are handling the unclean fault data. If you have sometimes if you get the data from the geophysicist, which is kind of unclean or kind of having a lot of complexity, uncertainty, many things, the structural framework model could handle that. And also one of these advantages it is linked to the seismic and good for ready fault model, so it is fast actually. The limitation, there is very limited, you have very limited control on it. They are very manual update, view manual update. And sometimes they are not ready for property. You need to go back again and convert it to the corner point gridding. So it's kind of one of these limitations, of it. So if you need the bottom line, you just this is the decision of choosing the method. It should be taken before you start the work, depending on your reservoir type, structural complexity in the subsurface. So there are many reasons. Many reasons to help you to decide which one you are going to use. So now the structural modeling, we start from fault modeling and then horizon modeling, zonation and layering. as you can see here. So once you finish, if we have simple model, we don't have fault here. So the top and base of the reservoir will be your horizon. These horizons are most of the time coming from they are seismic horizon. So you will use them as a horizon. And within these horizon, you have some formation tops picked from the logs, cannot be seen by seismic due to the resolution of the seismic. So you will have some picks in between, and you can use some isocoring technique to build these zonation so that you will have several zones in between. And once you have your zonation ready, you will go with the layering. You need to put layering depending on the resolution of the model you want to you agree with the reservoir engineering about, because this layering is very important when you upscale the property. If you have a porosity or facies, I mean, every cells will have one value. So the more layer you have here, the higher resolution you have, but not necessarily you need to have a lot of layer there. It depends on if you have like reservoir zone, non-reservoir zone. So there are different technique you use to I mean, optimize the total number of the cells you have in your I mean, geocellular model, because if you have more layer, you will have more cell, and then you may have some issue while doing the simulation later on. So you need to make a decision about this layering, depending on the agreement between the reservoir engineer and the team. And as you can see here, we have these constant number of layer, and here we have we have some truncation here, depending on your conceptual model. If you have pinch out, if you have truncation, so this is kind of more reservoir characterization, which you can agree with the sedimentologist and the operation geologist, the other team of the geologist who is in charge for that. You agree with them about a certain conceptual model and structural model. So then you, as a geomodeler, will follow what the concept is agreed with them. So now here, this is a question: corner point grading or structural framework. I mean, as I mentioned in the previous slide, it's a decision taken before you start. So if you decide to go with the corner point grading, you will start your work by modeling the fault one by one. And after that, you will start doing the pillar grading, as you can see here in this sketch. So the pillar grading is nothing but just making a skeleton framework consisting of top, mid, and base skeleton grid. So it's kind of a process used while doing the corner point grading. In addition to these three skeleton grids, I mean, as you can see here, this skeleton grid. In addition to these three grids, there are pillar connecting these every corner of the every grid cells to each other. And the reservoir is divided, I mean, the reservoir volume is divided into cells, as you know. So that's why we need to carefully consider this and make it we need to take time while doing it and make sure that they are having no problem and consistent. Then you will do a QC. I will show you the QC of the grid after in the next slide. And as I mentioned before, later during the property modeling, each cell will assign one value in this layer. So that's why you need to make sure that you do a proper gridding and pillar gridding, I mean. After that, you go to the make horizon and make zone and make layer. I already demonstrated it here. I mean, this is the layer you have here and zones, and this is the horizon. So this is the horizon coming from seismic zonation, coming from isocoring each of the formation tops we get from the geologist who do the well correlation using different type of data. It could be core, could be logs, but it cannot be seen by the seismic. So that's why you will get more horizon here comparing to the seismic. And then you do the layering. If you, however, decided to go with the structural framework, you will just start with your fault structural framework, fault framework modeling, as you can see here. And then you will go for horizon modeling, and after that you do structural grading. Not similar to the corner point grading. You start with the pillar grading, and then you decide your grid resolution. In structural framework, it is you finish from your structural framework, and then you will do the structural grading. So once you finish from your geocellular modeling, you need to do some QC. It's called geometrical modeling, in other words. So you need to make some structural modeling QC. So most software, they have a tool to check your grid and to check the suitability for resulting grid for further modeling. And maybe you can have some general rule here, kind of a checklist for the quality control for the geogrid. So maybe you can identify the maximum number of the grid in the vertical direction in each zone. So you identify that. This is kind of QC of your geocellular gridding. Also, you may consider plot distribution of the aerial grid size, dx and dy. Ideally, there should be a small variation in this quantity in the ideal case. If you have big variation, you may need to consider revisiting your gridding or building your geocellular modeling. Generally, you assume that you have uniform distribution. And also, you may also perform visual inspection of your fault representation and do in the 3D space you have in your software you are using. And one step, which is very important step, is checking twisted grid. This is most software provide a property you can create to make if you have twisted grid, if you have inside outside cell. So this is very, very, very important. You need to make sure that you have 0 twisted cells. I will demonstrate this in our demo. And here you can see that here there are some properties or some attributes you can take into consideration. While this is the twisted cells you have, you need to have 0 twisted cells. And there are some other property you don't need to have like negative thickness and concave grid. So something like that you need to make sure about it visually. And here you can see the grid orientation axis here. If you can see here, we have this is our grid, and typically we have the cell size 100 by 100 meter. Sometimes you go higher resolution, 50 by 50. Sometimes you go 150, sometimes you go 200. If you are in the flow dynamic modeling, you will have higher resolution. Not higher, bigger size of the cells, which mean bigger size of cell mean lower resolution. Higher size of the cells mean, bigger size of the cell mean that you have big cell, that mean you have lower resolution. If you have smaller size of the cells, that mean you will capture more heterogeneity, more resolution, so meaning higher resolution. So typically we start with 100 by 100 in the XY direction, and vertically it depend on the reservoir type. It could be it could be very high resolution, 1 meter, or it could be 5 meter or 10 meter. It depends actually. It depends on each reservoir you decide. So here we finish from structural. We assume that we cover the structural modeling and we have the geocellular grid. And now we start the property modeling with the facies. So the facies is referred to a physical, chemical, and biological characteristic of rock unit, which is influenced by depositional environment and post-depositional process. So facies is very important and crucial component of the 3D static modeling. So it's mainly focused in characterize the spatial distribution of different geometry and different sedimentary facies. Within the subsurface. And you can see here, for example, we have some upper, lower shore face and transition zone. These are one example of the concept model we are using to build the model. And here you have a 3D representation of of the 3D facies. And we need to, if you build the facies modeling accurately, you will capture the geometry, heterogeneity, and continuity of these facies. And also, hence, you will understand the flow, pathway, and barrier that will impact the movement of the fluid, such as the hydrocarbon or groundwater within the reservoir. So the reason of building the facies is mainly to simplify the property modeling as much as that each facies should represent unique petrophysical distribution. So to achieve this, we need to have a core data together with the wireline logs, and also we need to have facies scheme or facies catalog coming from sedimentologist, which will be representative of the conceptual depositional model. So in this step, we need to sit and spend kind of quite good time with the sedimentologist to decide on the facies distribution, facies model, number of the facies. I mean, some sedimentologists are very generous. They are giving you 40 facies or more than that, which is it's very difficult to build such type of facies modeling with this number. So you need to sit together with the sedimentologist and agree with him about the final number of the facies you are going to use to build your facies modeling. So you need to get a good discount with him, so that you can easily make a link between the facies, between the sedimentology background of the facies and the petrophysical property, including porosity, for example. So that's a kind of time you need to spend with the sedimentologists. And once you agree about that, you start with the upscaling of the facies and in the pre, or you build the model already. You have the geocellular model with you. You have the layer. Now you will have at every well you will have facies as a log coming from core. If you have small number of the core or small cold well, you may consider doing facies prediction in other wells using logs supervised by the core facies, and so that you will have better control and distribution the facies across your model. If you see here that, for example, here we have the facies logs here coming from, I mean, let me see if I have laser point. Okay. You see that we have facies logs here. This is the facies coming from the sedimentologist. And then here you have this is your cell's thickness, you see? This is one cell, and this is another cell, one cell, two cell, three cell. So this is the layers you have actually. And then, for example, here, you need to assign one value here. So you will use the technique while you're doing upscaling. It could be midpoint, it could be there are different algorithms we are using here. In this example, for example, they use, I think in this example here, they use most of, if you can see here. So they have like sand here and we have shale. And since we have the thickness of the cell is bigger than the resolution of the logs. So you need to choose one value, or maybe you can go higher resolution, but this is not optimum. I mean, in this case, otherwise it will be very high resolution. So it will be not good to go with such detail, not required or not very important. So you will upscale it to the most of facies, then you have sand here. And similarly, you do the same things here and there. And then, for example, here you have shale, and here you have sand, and then you have shale, and then you have sand. So filled your cell, upscaling or blocking, the facies. And you can see here from this, you can see here we have this color. You see the layers. We have the layers, and we have the layers here. Every layer is filled with the color facies. And we need to scale up, as I mentioned here, and we block them in terms of the process of upscaling from log to geological grid. And finally, you will have a result like this. For example, we have channel facies here, and then we have channel here in the upscale. We have shale, we have channel. something like that. And similar, this is for the facies logs. And similarly, we will have it for the porosity logs. Later I will discuss that, why we are doing the physical modeling. You upscale, every layer will have a certain value of the porosity, as you can see here, and similarly you're going down. So one important thing we need to consider is the geostatistics. We need to have very important or very strong, background in geostatistics, because it is applied. We are distributing the fishes using, yes, we have the logs, we have the seismic data, we have the core, but we need some tool to distribute this property across the 3D domain. So that's why we're using the geostatistic technique, or branch of the applied statistics that emphasize in the geological context. So using the statistics tools such as variogram, histogram to control the distribution of the property. So the variogram is mainly used for the spatial relationship between the data, because you have spatial distribution of the fishes. So it is, the geostatistical technique is very important part of the reservoir management, because it's quantitative numerical model are required for planning the field reservoir development to optimize the time, resource, and economic gain. So it is kind of very critical tool. So I will just briefly talk about it, and maybe this task is a very long task. If we keep talking about it, it will take very, very long time, days actually, to understand this concept. But it is very critical, and it is not that difficult to learn the geostatistics. With the practice, you will learn the theory, and then you will apply your knowledge, and you make some errors, and you repeat again until you master these tools. You don't need to be very, very advanced geostatistics, but you need to have a good background to help you to better understanding the tool of the geostatistics, so that you will build kind of a good property and fishes modeling. So we have two terms here, as you can see here. We have estimation and simulation. If we look at the data, we have a data as a point, for example, here. And if we need to predict what is in between the point, for example, let's assume that they are the wells in between the data, and we don't know that what is going on in between. You may do some estimation, or you may do some simulation. So if you do the estimation, in the estimation, you will just find the very close, you will just draw the line and as closest as to the point. And this will be kind of not necessarily to be very close to the reality. If you look at the reality here with the solid line, they are not as regular as you are expecting by doing estimation. So it is better to do in this case, to do the simulation, because the simulation is honoring the mean and the covariance and the histogram of the real value. So mean, covariance, and histogram, and they are coming from the geostatistic background. So you need to understand what it means by mean, covariant, histogram, variogram. All of these details, I strongly recommend to learn it properly, so that you know how to use these tools to help you, in your work and task in building in the static modeling. And you can see the simulation here is more closer to the reality. The simulation here with the dashed line, it's more closer to the reality. And also in the simulation, you can build different realization. So you may somehow get to the reality, or very close to the reality. So that's why it is good to use the simulation rather than estimation. So in the variogram side here, you can see here we have different terminology in the variogram. So the variogram is a tool to help you to to look at the degree of the difference between two collection of the data. It's having some attributes here. You have lag distance, which is the separation distance between the 2 points. So you may consider a 2 point, or you may consider between one first point and third point. So you call it 2 lag, or maybe you consider third lag. So it depends on your decision. And also for the cell, I mean cell is the variance at the point where you have the range. And the range, the most important thing here in the variogram is the range, because the range is correlation distance. So that means if you have, let me demonstrate it here in the next slide. I think it's better. If you have, for example, if we have, this is a channel. If you have big range, that means we have less variability, right? If we have big range, we have less variability. If we have a small range, like in this case, we have high variability. Why we have high variability? Because we are starting from muddy facies, and then we're going to the silty facies, and then we're going to the channels, sand, and then back again, and etc. So you have high variability here. And this is, we call it minor direction of your histogram, sorry, of your variogram. So the range in the major direction is always bigger than the range in the minor direction. Why? Because across the channel, the system, correspond to the major direction of the, and the degree of the dissimilarity is very low. Hence, the variance will be very low. So you have a big range here. So then that means each facies are linked. Big range, you mean that the relation is bigger. And then let me go back here, and that's a slide to demonstrate it better. If we have bigger range, so that means the relation will stay exist, because once you reach the cell, there is the relation between the two data sets will be no relation. So if you have big range, you have that means you have more relation. And then, as I mentioned here, this is the big range, mainly with the major direction of the histogram. And we have, okay, more similarity, meaning that you increase the range, yes. And we have 3 common type of the histogram. We have spherical histogram, we have exponential histogram, and Gaussian. Spherical histogram is kind of a general, good general histogram algorithm. And exponential histogram, which is in the middle, it's most of the time it's produce noisy result. And the Gaussian histogram, which is here, as you can see, it's give you very smooth results. So this is type of the histogram you need to model before starting the property modeling, and you need to consider these concepts: bigger range, smaller range. This is the most important thing. Most of the time, the software will help you in this, but you need to have a good understanding of it. So in summary, for this subject, the closer the 2 points are to each other, the more similar. This is the concept in general. They are expected to be. And in the data analysis, you can also use the histogram of the properties and will indicate you the number of the pairs you are going to use. And I will demonstrate this in the demo. Maybe you will have a better understanding later. So here, after we finish, maybe one slide more here. Yes. So we have 2 types of simulation. We have, we have stochastic simulation and we have deterministic. Which range, which algorithm we are using in building the facies? The general rule of thumb: if you have higher number of wells, higher number of data, huge number of data, you can estimate. You can use estimation, which is equivalent to the kriging or deterministic, and it will give you a very smooth result. However, if you don't have if you have low number of the data, you consider having simulation, and you consider getting multiple realization, and I think there is a question here. Someone raised his hand. Anyone raise his hand? Maybe we can keep the question at the end of the lecture. Okay, and okay, we go simulation kriging. So the output will be many in the simulation. Simulation, which I'm stochastic, and the kriging will have one model, and the property. I mean, of course, in the both of them, they are going to honor the wells and variogram, but in the simulation, you also honoring the histogram. So this is kind of advantage for simulation. And also in the image, it's having high noisy variability, many things. And the kriging, you have smooth. You can look at here in this picture, you can see the kriging, the red one is very smooth. Whereas the simulation, which is the dash green one, it's very, noisy or busy or kind of, which is actually the reality in the subsurface is very heterogeneous. So that's why the simulation is always, most of the time, is preferred. Unless if you are having huge number of data, you are very confident, you are sure about your analysis, then you may go for the kriging. And also the simulation is used for flow simulation and for the uncertainty calculation. Whereas kriging, or deterministic approach, is using mainly for mapping and volumetric. So the next slide, this is the last slide of the theory. Stochastic simulation versus stochastic simulation versus deterministic. So in general, the definition of you need to have a balance between the determinism and probability. The underlying design issue. We stress in the balance. You need to use both of the tool whenever you feel better to use to have a balance actually. And especially when you have you may lose. You can use the probability, yes. If you have a huge number of data, you can still use the deterministic, but you need to have the balance. If the determinism is aspect of model which is fixed, it is fixed kind of one realization on the model and absolute. If you place the fault, you place it here. There is no range of uncertainty. Whereas in the probability or stochastic refer to aspect of the model which is specified by random stochastic outcome. And stochastic process. This word is by origin is coming from the Greek, called stochas. I don't know if we have any person from Greek or know that language, which is meaning that aiming or guessing. So stochastic meaning that you are guessing or aiming. So it is one whose behavior is completely non-deterministic. It's kind of guessing or aiming. So probabilistic method is likely of the, similarity of the probability theory. And it's kind of, one of these methods is a famous one. I will talk about it in the volumetrics uncertainty, called Monte Carlo method. And this is referred to especially in relation relation the uncertainty, handling the uncertainty, and are a class of algorithm that rely on repeated, it's kind of repeated the random sampling to complete the probabilistic results. So this is the general rule of the probability. So this is a kind of a general theory about the Facies modeling. I think if you have more questions, maybe we can discuss after. And in the next slide, I will just show you quickly the method. And the deterministic, I already spent quite a long time in explaining the deterministic meaning. We have different algorithm. We have estimation and or direct addressing. Estimation is the cracking. I mean, cracking is coming from the South African scientist. His name is Crick in the past, who back to the history, who developed this tool. That's why they call it cracking. And it is kind of discrete distribution is a property honoring the predefined histogram. And this is kind of giving you one result. In the direct assigning, you assign value, or interactive. Assigning value, for example, you know, in the model, you know that we have this layer have shell, you know that, and sure. So you then assign one value. Interactive, you can use your manually, you use your paint faces to directly draw your faces. And all of these tools lie under the deterministic method. We have learning system, we have neural network. This is mainly, we are using in the modeling, but mainly used in predicting, for example, the faces. And they are using neural network, which they are classify the model based on the train estimation model process. And we have the stochastic method, which is widely used in the faces modeling. And we have the most famous one, this IS model. It's mainly used to honor the input distribution and direction setting, like variogram and trend. Also, we have truncated Gaussian. It's used where the faces are known. If you have sequence of the faces prograding or retrograding, you can use the truncated Gaussian. You can use it also with the trend. Also, if you have trend map, you can build some trend map, or you can get it from the sedimentarist and use it together to distribute your faces. And we have another tool called multi-point faces simulation. That all are located under the pixel-based model, but these three are using a 2-point faces model. Here we have multi-point faces model, more than 2 points to distribute your property. So what is the difference between here and there? Here they are, rather than using those three methods, they are relying on in the variogram. Here in the multi-point faces simulation, they are using training image to describe the spatial correlation. So it is based on the training image and distribute your faces based on the training image you provide. And the final method here, the object-based method, it's mainly used in the fluvial and karst reservoir. So it's allow you to populate a discrete facies model with different bodies and various geometrics and facies distribution. So it is kind of advanced work here in the object-based model. You need to consider a lot of property. You need to consider a lot of items to, you like, for example, your channel angle, your channel, direction, many items you take into consideration. You need to sit closely with the sedimentarist, and it need a lot of iteration to go back and forth until you get the final model you like. So we finished from the facies modeling. Now we are in the property modeling. The property modeling is mainly facies. Is mainly porosity, permeability, and water saturation. You know here by the definition, porosity is the fraction of the unit volume filled with the pore, and it is how likely the storage, how likely the rock is store your fluid. Permeability is how likely the rock transmit or flow the fluid. And in the water saturation, it's kind of fraction of the pore space which is occupied by the water. And you can see the sketch here. We have matrix and fluid. We have the matrix, oil, and water here. And then we have the flow, coming, which is permeability, which is a dynamic. Actually, permeability is not a static property, it is a dynamic property, as it is having 3 components. We have vertical permeability, we have X and Y permeability. So it is not like porosity, it is dynamic. Porosity is static, whereas permeability is a dynamic property. So similarly, we have method of modeling. We have deterministic, we have cracking, we have different types of cracking here. We have interpolation also, moving average and functional. And we have deterministic, which is you have assigned value. And we have, still we are in deterministic, I think, yes. We are still in deterministic, assigned value. And we have also artificial, work. We can use it also for physical property. And we have stochastic. Stochastic, which is the pixel-based, we have two common methods, which is the SGS, which is a sequential Gaussian simulation. And we have Gaussian random function simulation. Almost they are similar. There are some small differences between them. It's but however, in the Gaussian random function, they are faster, and it's give you a good, better variogram reproduction. And if you have some advanced collocated and co-simulation option, so random function simulation is better. SGS is kind of classical way of most geomodelers are using it. It's kind of classical way of distributing the property modeling. Now, in general, if we are, if you are in the early stage of the exploration, you consider going for stochastic. If you go more data, you have more data, you go for objective. And similarly, object-based, sorry. And then you go to deterministic when you have huge number of data. This is kind of a rule of thumb you may consider to which algorithm or which method you are going to use. Here, property modeling, you see that we have 3D structure model completed. Then we do some data preparation, QC, and analysis. Then we scale up the wheel logs in the cells, the layers we already defined. And then we have data analysis, variogram, histogram, PBS, vertical proportion curve, many tools you can use in data analysis. Then you do the facies modeling. And finally, you have the metaphysical modeling, deterministic or stochastic, depending on your, choices. Here you have why we have modeling as you can see here, why we are modeling the faces. It's if you look here in the upper image, we have porosity, upper image, porosity built only with the logs without faces. Here we have the faces in the middle image, and in the lower image, we have the faces, we have property modeled after we model the faces. So if the upper porosity model is kind of, if you consider it reasonable representation of the field, then you don't need to do a facies modeling. However, if the porosity distribution is believed to be, significantly impacted by the distribution of the faces, then, or you have a strong relationship between your, property and the faces, it is highly recommended to model the faces and spend time doing the faces modeling. And you will have better results as your faces will drive your distribution of your property, porosity and permeability. So now I discuss more about porosity modeling and permeability modeling. Now I will talk generally. If you have, for example, normally in I don't know if we can draw here. Then normally in the you have if you have logs from the petrophysicist about the permeability, then you can use similar approach of modeling permeability, and you need to just co-click this permeability to the porosity. Co-click, you are using porosity as a secondary variable to distribute your permeability. If, however, you don't have kind of that logs, you can just build kind of relationship, as I'm drawing here, between porosity and permeability. Most of the time, the petrophysicists, they are doing kind of rock typing here. So you have different rock type or BRT, petrophysical rock type. You may have 5, 6, depending on the petrophysicist. And each of these rock type, it has equation, like here. This is the equation. For example, he starts with RT2, for example, and he have this equation. So then you already have your porosity as a 3D property. Then you just use this equation, use a calculator. I will show it to you in the demo. Use a calculator to build the porosity. So this is how we to build the permeability. This is how we are going to build the permeability in general. And now water saturation is similar way. You will have also equation, as you can see here. The concept of the water saturation, it's there are different approach to build the water saturation. Mainly they are using saturation high function. And you can see here the relation between saturation, here is W, and the height. The height which is high above free water level. For example, if you have reservoir here, and then you have free water level here, or oil water contact, this is the height. I will also show you the demo of this one. This is, we call it high above free water level. So this is how we are building the saturation. It's we need to model it using the saturation high function, which is derived from the logs and core analysis. They are doing some kind of scale analysis. Special core analysis lab in the lab analysis, and so it is modeled in the last. And as I mentioned, the saturation equation may be provided by petrophysicist and a laboratory provided scale report and by the team. So then you do it similar way. You did the variability using the equation. So initial saturation is predicted by reservoir rock type. Every rock type have different equation with a specific porosity and permeability based on the saturation and the capillary pressure relation. So this is how we are modeling the saturation. And here, this is another concept of the high above free water level. We call it high above free water level. So it is between the oil water contact, or maybe between, it depends if you have big transition zone or not. It depends. So it is kind of between free water level to the structural, to the top of your structure. If you don't have gas or something, you may have top of the oil. In general, hydrocarbon. So it is this distance between this one here and this in the top of the reservoir. So where you have hydrocarbon column. And here we are using the equation of the, in petroleum engineering, there is a different equation, dimensionless function of water saturation. And it is an attempt to extrapolate the capillary pressure data for a given rock that are similar. So which is every rock type have similar equation, and they have similar porosity, permeability, weighting property, and all of these things. So then you get that equation, but it is kind of a teamwork between you and the petrophysicist and maybe reservoir engineer to use the equation to model the saturation. Now here we have the equation, example of the equation of the water saturation. You can see. So this is the equation of, for example, if you have clean sand, you are using different N value. If you have radioactive sandstone or silty shale, so different reservoir, they have different equation. And here you can see the equation we can use for each of them. I will demonstrate that for you, but we will do it in one equation, because if I do all of these equations, it will take, we will finish tomorrow. Okay, so I will just, I'm trying to finalize the slide so that we go to the demo. So here we have the water saturation, rock type, porosity, permeability, water saturation, and here I have a cross section. This is an example. And finally, we have the volumetrics, which is a crucial component of the 3D geological modeling. We have different method of the, volumetrics. we have volumetric method, which I'm going to demonstrate that. This is the common method used for estimating the hydrocarbon in place. Also, we have material balance method. It can provide a reliable estimate of hydrocarbon initially in place if you have mainly in the mature reservoir. We need to have a lot of data from production history. Also, we have decline curve analysis. It's a popular method for estimating reservoir reserve by using assumed recovery factor. You using some curve, decline curve to get your volumetric. And also you can use analogy. This method is most useful when you want to have economic, when you're running the economic on the current field, you just need to get analogy. And also if you want to compare factor that analogy and current field or wells, this is another method. So in the volumetrics, we use this equation, hydrocarbon initial in place, we do the GRV. The GRV is the rock, everything above the free water level. So it is GRV, which is called gross rock value or gross rock volume. Sorry. If you multiply that by net gross, so net gross, it's kind of percentage, or maybe it kind of cut off. You put for porosity and permeability. Let's say I don't want to have porosity less than 5%. For example, I will consider it non-reservoir. It depends on the reservoir type. So you multiply it, then you will have your net to gross value here, which is here. Net to gross volume. After that, if you multiply that by the porosity, you will get net bore volume, which is here. And then if you consider that with the oil hydrocarbon saturation, which is 1 minus water saturation, you will get hydrocarbon bore volume. We need to consider something called the volume formation factor to get, because the pressure, the oil and the subsurface having certain pressure condition. So we need to divide that by the B0, B0, which is volume or factor, factor volume, formation factor, volume factor here. So you divide it so that you will get your STOIP, which is standard oil initially in place under STOIP condition, under surface condition. So which is the stock tank condition. So you divide it by the FVF provided by the reservoir engineering, and we are going to use this equation in the demo. I think it is already 1 hour, and I want to cover the uncertainty. I'm just wondering if we can go with uncertainty. Maybe I will just go very quickly with the uncertainty, and I will demonstrate it. And maybe we can have another session for uncertainty in detail. So it is better to have uncertainty rather than just something in reality, illusion of reality. This is said by the Andre journal. And when we do the uncertainty, it is the lack. What is the definition for uncertainty? That you are not certain. There is lack of certainty in describing an objective. So we need to have uncertainty. So we start with the base model first, and then you run several uncertainty. It applies to prediction of the future event. The more hard data we have, the less uncertainty we have. Calculating the uncertainty in the model tell us how realistic is our model. So that's why we are doing the uncertainty. If we go here in the next slide. So why we do the uncertainty? We need to know how much oil exit in the range. We need to know how much we can produce. We need to know what are the main source of the uncertainty, which factor in uncertainty. That's why we are going to do sensitivity. Is it porosity? It is the oil water contact. It is the facies. There are different types of sensitivity analysis. You need to know which are the main source of the uncertainty and how they impact our estimate, how to account for them, to evaluate the risk and to make a good decision. This is why we need the uncertainty. And here we are doing the kind of uncertainty in the seismic interpretation, in the velocity model, in the log data processing, in the data analysis, also in the 3D interpolation. This is how we can do the uncertainty. This is type of uncertainty we are doing. And maybe Yeah, and it is better to have different realization than one. If you look at the yellow curve, this is the reality. If we do actual, if we have one single scenario, we may not cover the actual. But if we have many realization, you see the actual is lie in the between. So one of these case or one of these realization will be very or almost together with the actual case. And then here we have the uncertainty sensitivity. Sensitivity, this is a tornado plot to know which factor have more influence in while doing the uncertainty. Is it the gross rock volume? Is it the net gross? It is the porosity? It is the, I mean, formation volume factor? Is it the recovery factor? Is it the saturation? Which one is having the more impact? In this example, you can see the GRV having the more impact. In the uncertainty, you have your B90 and B50 and B10 here. As you can see here, you give your team or management different, range of volumetrics so that they can help them to take the decision. And finally, final step here, we have the grid upscaling. This is the final step you are doing in the static model. As you can see here in the static model, we have fine scale, and we are upscaling it for simulation purpose. So geological grid upscale is the process used in the reservoir modeling to convert the fine scale geological grid into coarser grid without losing any essential geological. It is you need to be careful. You don't do upscaling blindly. You need to do certain analysis to do it so that you will maintain the accuracy and of the representation of the reservoir heterogeneity. And here I have a reference for my slide and the book. I recommend you to read it. We have, you can look at them, Reservoir Model Design by Philip Ringoros, and Data Analytic, Geostatistical, and the Reservoir Characterization and Modeling book. Also, Steve and Cameron have a nice book in Reservoir Modeling, a practice guide. And also I use some manual from Schlumberger, and also I use some post and videos from our friend from Petroleum Engineering Association. And the conclusion here, this is the last slide I have. How to model the experience. It's kind of very, very, you need to, 3D geological modeling is a powerful tool that enable a comprehensive understanding of the subsurface. So you need to make, you need to leverage your experience using advanced modeling technique, informed decision-making, continuous involvement, multidisciplinary collaboration. The geomodeler is always lie between different type of people, geophysicist, petrophysicist, geologist, reservoir engineering, sedimentologist, stratigrapher, economists, sometimes managers. So you need to just have the skill of align yourself with all of these demand and these need. So you need to understand, characterize, and model. So always we say that there is no right model, in general, but there is a good model. So nobody can predict the subsurface, but simply understand the complexity of nature of the model. It is quantity and model, to quantify it, and the model is simpler and more sensible. This is the last slide for me. Thank you very much. And I'm just wondering if I go to the demo or not. What do you think, Nikhil? You see my screen?
Yes, yes.
Okay. Maybe you see it now, you see the better. Okay. So I will just make a demo. Let me just put a new. So now if we want to build a new model here, I will just go right away to the model, insert it here. And then, let me just, okay, I will define a model here. right? And I will call it demo. All right, we have the model here, and then we will, as I mentioned to you, I'm going to use simple grid, if otherwise it will take a lot of time. So we will build a grid, for example. Let's just do something like this here. Here we identify the number of the cells. Let me just choose one of these surfaces. Geometry here. Right? So I choose the geometry from this surface, and then I will identify the 100 by 100. Okay? And then I will have my grid here. So if I display the skeleton, you see, this is the skeleton I mentioned to you, the mid, top and mid and bottom. And then now I need to fill the horizon here in between. So I will go in the horizon modeling. And then I have 3 horizon here. 1, 2, 3. And I have these horizon. I choose this so that it will choose all. And then I will choose the tops. Targets. And topness. This is the tops. And top it is. Right? I don't have faults. It is just a model. And then let me just make it small. And I apply. Now I don't want the skeleton, I want the horizon here. Before I don't have horizon, now I have horizon. I have horizon here, as you can see. This is my horizon, huh? Okay. Now I want to, let me show you something here in the slide. I want to do something like this for you. Something like this. You see, we have top. Here we have 3 horizon. Here we have 2 horizon. I will have zonation in between. Then I will go in zonation. I will choose above the target. I don't have zone. I have zone here in between. I have 2 zone. So I will use the isocalling thickness map I have here. And then I will choose this. I will put them here. And then I will have the formation tops of the parts. Right. So then if I apply, just I want to use the similar way I did. If I apply here, you look. Now I have 2 zone. Right. And then I have another zonation here below this. I will go below this. Right. I have nice thickness map, and then I have it here. These 2. And then I have top these 2 here. And then I use it from the horizon modeling. I don't want to. Now we have more zone here, we'll see. Okay. Now I finish with my zonation. I will cancel this and I will cancel this. I have layering. And the layering, it depends on the resolution. If I want to have many layer here, if I want the resolution to be high, I increase the number of layers here. So one way to decide if I want to have it 1 meter, I will just run it as is. Okay. Then I go to the zonation I created, and I go one by one to see the thickness or the average thickness it gives me, which is 16 here, right? It is 16 here. So I put a 16 because I need to have I want to have high resolution. Right? For example, if you look at the model here, if you want to look at the resolution of the model, you go to the 3D grid and go here. The resolution is 100 by 100 and vertical resolution is 32. I want this resolution to be 1 meter. So then I need to have 1 meter resolution. So I need to, for each layer, I need to create certain number of, for each zone, certain number of layers so that this will be 1. Now it is 32. Let's keep it here. And then let's go layer by layer to see how many. For this one, target 3 is needs 16. For target 2, it needs 33. And for target 1, it needs 22. And for this one, it needs 42. And for this 2, it needs 45. Right? Now look at this. This will change to 1. Yes, it is 1 now. Okay, now I have high resolution. And now you see, I have high resolution model. So, right. So, Nikhil, I think it is already 1.5 hours. What do you think? Should I proceed? Or we can make it another time?